Alright, welcome to Chapter 7. This one's on exponents and exponential functions. This is actually one of my favorite topics of the year, so I hope you can find it as interesting as I do. Starting section 1, this is going to be multiplication properties, so we want to learn to extend our idea of exponents that we had in previous years, so we'll first do some vocab and then lots of examples. First is a monomial. So a monomial, mono means one, and nomial basically means numbers. So a monomial is a single term with numbers and or variables with positive exponents. So what this means is, for example, 3x squared. That's a monomial because it's a single term. You can have a product multiplication between two things, but you can't have addition or subtraction. So that's a monomial, but 3x plus 5, for example, is not a monomial. That's a binomial. Okay, next vocab word, a constant. A constant is any monomial that's a real number, so it doesn't have any variables. So 5, 7.2, 6.3, all those kind of things are constants. They don't have a changing value. A linear expression. This is any expression where the exponent on the variable is a 1. So for example, 3x squared is not a linear expression because the exponent is not a 1. 5x, that's a linear expression. 3p, that's a linear expression. Negative 7q, that's a linear expression because all these, even though we don't write it, they all have a variable of a 1. Now, even if I had 5 squared times y, that's still linear because the variable, which is the y, has the power of 1, even though the numbers doesn't, because this can be simplified to just 25. A nonlinear expression is any expression where the variable and the exponent is anything else besides 1. So it could be positive, larger numbers, or it could be negative, or it could be a fraction or a decimal, something like that. And lastly, an exponential expression is something that looks kind of like what I wrote up here. You've got a number in the front, which is called the coefficient. You've got the base, which is typically a variable. And then you have the exponent, which for now is going to be a number, although we'll see later on this year that that could also be a variable. So a base and an exponent and a coefficient in the front. Alright, there are some rules that we have when multiplying and dividing. Well, we'll do multiplication first, multiplying exponential expressions. Now, remember that these only apply when you're multiplying monomials. So, here's a monomial, here's a monomial. When multiplying, keep the base the same. So if our base of our exponents is x and x, it stays as an x. But we multiply the coefficients. This is because the first monomial, ax to the n, the a and the x to the n, they're multiplied together. And the b and the x to the m are multiplied together. And with multiplication, you can do them in any order. So the a and the b get done first, and they become a new coefficient at the front. Then x to the n and x to the m, those are our exponential pieces. When you multiply two exponents with the same base, you add the exponents. So for example, 3x squared times 8x to the 5th equals 3 times 8 is 24. X squared times x to the 5th, we keep the base the same, but we add the exponents. 2 plus 5 is 7. And what you've learned last year about exponents is that an exponent represents the number of times you multiply something. So you could think of this here as 3 times x, that's the first part. Second part is 8 times x 5 times. Okay, and now if you multiply these together, you have still a 3 and an 8, which is 24. And then how many x's are we multiplying? You just count them up, 1, 2, and then 5 more here. So the total number of times you multiply it is just adding those two exponents together. And that's kind of the shortcut or easy way to remember this rule. So the rule is, if you multiply the base, add the exponent. But the reason it makes sense is you can write it out longhand, and you can see that's how many times you're getting multiplied. Therefore, that's the new exponent. Okay, the next one is a power of a power. So if you have an exponential expression raised to a power, you multiply the two exponents together. So x to the n, already an exponential expression, raised to an even higher power, to the m power, you multiply those two together. So for example, 3 to the 5th to the 3rd equals 3 to the 15th. And it doesn't matter if the base is a number or a variable, the exponent rules apply the same no matter what. Okay, the reason, again, why this makes sense is you can just go back to that definition. The 3 to the 5th we can think of as our new base, and when we raise that to the 3rd power, it means we do this operation 3 times. So because this is cubed, that means we do it 3 times. And each one of these, right, I'm not going to write all of them, but each one of these is 3 times 3 times 3 times 3 times 3. And then we have another set, and then we have another set, and we end up doing it 15 times. So, grand total there. The shortcut is to just multiply the 2 exponents together. Alright, the last one for this section is distributing a power. So if you have a monomial raised to a power, every factor in that monomial gets raised to that power individually. So another way of saying this is that you distribute the exponent in like this. Okay, the problem is that this only works for monomials, and you'll be tempted to use this shortcut even when the stuff inside is not a monomial. So be extremely careful. You only distribute the exponent in for a monomial. So each of these inside already has a variable, a base, and then the exponent, because it's not listed, is just a 1, right? So c to the first, when you distribute an n there, you now have an n and n. So just be cautious that if the stuff inside already has a power. Let me give you an example. So say we had c times x squared times y all to the n power. You distribute this in. When you distribute, it's a power c to the n. Great. But now when you distribute here, this is a power of a power, and we learned from the previous example that a power of a power you multiply, so 2 times n. So you have x to the 2 times n, which is just 2n. And then here, y to the n. Okay. So some problem solving tips, then we'll do examples. Remember that we're simplifying expressions here, so we still follow PEMDAS. So if you have parentheses, you want to do those first if you can. Then of course all your exponent rules, and then multiply and divide. So the exponent rules apply to multiplication and division, and there shouldn't be any adding and subtraction, at least right now, because we're dealing with only monomials. So be careful that you apply these, like I just said, only to monomials. If you have a binomial or a trinomial or something else, you can still distribute, and we'll learn more shortcuts and tricks for polynomials later in this chapter. The second or third thing here that I want to emphasize is you could memorize all these exponent rules, and you should memorize them, but most importantly is that you understand why they work. And to understand why they work, you can always go back to that just definition of exponents being written out the long way. So for example, x to the third really does mean x times x times x. And so if you're ever unsure what that shortcut was, or you forgot, or you want to double check, you can write it out the long way and figure it out. Remember, an exponent means the base is multiplied that many times, what I just showed you right here, so you can always write it out. Okay, so we're going to do some example problems. I'm not going to do all of these, but I just screenshotted it. And then we will move on to the next section. So first, determine whether each expression is a monomial. The first one, the answer is no. And the reason why is because even though division is okay in a monomial, you can't have a variable in the denominator because, oh, you haven't learned this yet. Okay, so for a monomial, you can only multiply variables together. So the fraction in the front, 21 over 7, reduces to just 3. And then you have a squared. So that would be a monomial, but then when you divide by b, it's no longer a monomial because it's a fraction with a variable in the denominator. So we say no variable in denominator. Okay, the next one is a yes, because even though we have a denominator, it's just a number down there, and so we have our variables in the top, and no negative exponents, which we'll talk about in the next section. Okay, so variables only in the numerator, and a single term multiplied or divided together. Alright, simplify each expression. Here we have a group of variables and coefficient. So 2 monomials multiply together. This coefficient is -5, this one is a 3. So when we multiply this together, we get -15. Now we have x squared multiplied by x to the 4th. That's going to give us x to the 6th, because when we multiply this 2 pieces with the same base, we add the exponents. Here's a y to the first power. There's no y's over here, so we have just a y to the first power. And you don't have to write the first power, obviously. And so that's all there is to these kind of problems. same base, keep it the same, add the exponent. The easiest ones to mess up on are if they have no exponent shown, then you have to remember it's a 1. Okay, let's try the next one here. 3 times negative 2 is negative 6. A times a squared, so this little a is to the first power, so that's an a, and then there's 2 more here, so we have a grand total of a to the third. Then we have d to the fourth, and there's no d's here, so we have d to the fourth. We don't add anything to it because there's nothing to add to it. Okay, next one here. Negative 15 and negative 1/3. That's negative 15 divided by 3. Negative 3. So that's going to give us 5. We have an x here and we have an x here. So that's x to the first multiplied by x to the first. X times x is, of course, x squared. And then we have y to the fourth and y to the third. 4y's and 3y's combines together to give me y to the 7th. Okay, and I could keep going, but for the sake of time, I'm not going to do too many. Let me just jump here to a different style where we have a power of a power. Like for example this one, we have a 1/4, an a, and a d. So this is going to distribute in to all 3 pieces. And you don't want to forget the number at the front. So we have 1/4 squared multiplied by a squared. And then this is multiplied by d cubed squared. Okay, so 1/4 squared is 1/4 times 1/4. That's going to give you 1/16 times a squared, d cubed squared. Now remember, this is a power of a power, so we have d cubed, and then we have another d cubed for a grand total of d to the 6th. So final answer. And don't be afraid to write these out in a couple of steps. There's no reason you need to do them all at once. Another thing is, if the answer is expressible in simple numerical terms, you can do that. But if it's going to be a really big number or a really small number, you can leave it in exponential form. So for example, 1/4 squared, it's okay to just write 1/16. But here I have 4 squared squared. So this inside part here, a power of a power, gives me 4 to the 4th power squared. And that's going to give me 4 to the 8th power, because again, a power of a power I multiply. So my final answer is great to just write as 4 to the 8th power. I could have written the inside, and thinking of PEMDAS, 4 squared is 16. So I would have had 16 squared, and then I have to do 16 squared, which is going to be a really big number, I think 256, right? So that's 256 squared. So it could be going this way, and I don't know what 256 squared is. That's a crazy big number. And so when the answer gets so big like that, it's often better to just leave it in exponential notation. So this will be it for section 7.1, multiplication properties and powers of powers. Remember that keep the base the same, add the exponent, and move all the coefficients to the front. And we'll continue on with more exponent rules in the next section.